So my name is Berend Smit, and I'm working in the chemical engineering and chemistry department on campus, but also in the material science division. And I would like to discuss a little bit about our work we are doing on carbon capture. So during these carbon cycle 2.0, these type of diagrams have already been shown. And here is the one we are interested in, and that is here you see the emissions of carbon as a function of time. And what you also, here you see the differences between the carbon emission by petroleum, coal, natural gas, and cement. And it is sort of striking this sort of enormous increase of the emissions. And the idea of carbon capture and sequestration is to try to reduce these emissions by capturing the CO2 from, say, flue gases and storing it somewhere. So if you look at it at the, this is a slide from April, at the sort of emission sort of predictions if we don't do anything, that is sort of steady to increase. And here you see the various ways where you can sort of reduce the emission from the projected level to something which is slightly more acceptable. And what you will see in this slide, so this is the contribution of energy efficiency. The green one is renewables. This would be increased nuclear energy. And the orange part is what you can actually do by capturing the carbon by continuing using, say, fossil fuels. So what you actually see is this is the largest fraction, or a very large fraction, of what you can do to reduce emission is actually capturing the CO2 and storing it somewhere. So in this aspect, and you can also see that within these predictions, fossil fuels will remain actually for quite some time an important component of the energy production. Whether you like it or not, I think that is a very realistic scenario. So in that aspect, capturing the CO2 and storing it will be an important way of reducing CO2 emissions. So this slide is actually showing what you can, from all the carbon emissions, you have part which is, say, non-stationary sources, say cars or airplanes. And with there, it's very difficult to develop the technology that captures that part of the CO2. So what you have here are stationary sources of CO2 that are things that do not move, like power plants or cement factories and those kind of things. Well, there you can actually put the technology in place for capturing the CO2. Well, on this graph, you actually see what the different contributions are from these addressable sources. And you see the large fraction is actually power coal. And that's sort of interesting to see, to realize, because on say this graph, you see that natural gas or petroleum and coal, they have about the same, of petroleum and coal, they have about the same emission. But if you look at this particular graph, the largest fraction will be caused by coal. And the reason is if you burn coal, it's far less efficient. So it's emitting about 4 times as much CO2 compared to natural gas. So coal, and especially the increase of coal, which is actually predicted, is this very large source of CO2 emission. And that is particularly important to capture that part. So what is the idea? Is you have here a power plant where you do you have the power plant, you do the separation, and then you use geological storage. And geological storage will be actually the topic of the next presentation by Don De Pablo. So from a scientific point of view, which is a sort of interest, there are actually 2 issues here. Is if you, and I will go into some details about that, the capture is a relatively expensive part of this operation. And the geological storage, that contains actually many uncertainties, in the sense you put the CO2 under the ground and you need to make sure it actually stays at the place where you hope it will stay. Well, this is something which is addressed in the Energy Frontier Research Center of Don De Pablo. So if you then here, this is a prediction of the costs. So here you have from McKinsey, where you have the timeline, and this is in euros per ton CO2, and this is approximately the cost where you would like to have it, around 30 euros per ton CO2, and these are the current cost, and they're actually on the upper side of 90. So if you then look at the partitioning of the cost, you see the capture has the largest part. Transport has also some contribution because you capture the CO2 at a particular site, but that may not be the site where the storage is there. So you have to do this transport. And then here the storage, you can see it's a relatively cheap operation compared to the capture. Another interesting question you can actually pose is it not sort of wasteful to actually take the CO2 and just put it under the ground? Can we not do something actually very useful with it? And this is based on a calculation which Abhijit Brown did in April. And he had the idea, we just take a CO2 molecule and we attach it to some kind of chemical. And this makes a marvelous molecule which we call dreamium. And we're trying to actually sell this dreamium. And here you can find some of the applications of dreamium. Well, if you do that, it's very simple. The chemistry has not been developed yet, but it's very simple. You take CO2, you connect it to a molecule, and you get something very useful. If you think about how much CO2 is actually emitted per year, you can compare that with the total amount of chemicals being produced in the US. And here is a list of the top 10 chemicals, sulfuric acid, nitrogen, ethylene, oxygen, lime. And these are the number of tons that are actually produced per year. Well, if you add something up and you make this chemical bond, you'll actually see that you can only capture 0.5 gigaton per year, while the emission is 30 gigaton per year. So basically, if you do this calculation, any useful molecule, this dreamium molecule you will make, will completely saturate the market, but it will also deplete all chemicals being produced. The other thing you have to realize that CO2 is actually, from an energy context, sort of the lowest molecule, the lowest you can get. There's only one step lower, and that is actually mineral formation, and that is something eventually what will happen down on the Earth. So with this sort of background, you see the amount of CO2 is actually so enormous that if you make a particular application of it, it will completely saturate the market, because there are not so many applications you can think of. These are the top 100 chemicals, and it's only a fraction you can capture with these chemicals if you convert it into something useful. So with that, you almost get into the conclusion that the bulk of the CO2 you need to store at an environment where you do have the space, and the space is actually geological storage. However, you can also argue that you don't want to rely on a single technology and a single option. So all the other efforts where people are thinking about biosequestration or chemical conversions may actually be very important, but they may be sort of a niche market in the sense that the bulk of the CO2 you cannot capture in that way. So in that aspect, storage is an important component. I mentioned that it's a very expensive technology. So here is the current technology. So what you do is you have gases from a power plant, it's CO2, nitrogen, some water. And here you have an adsorption tower with amine solution. So what you do is you bubble this. Through here you have the amines, and the amines, they bind the CO2. The problem actually with those amine solution is that they can only contain 20% of amines, so 80% or 70% of that order is actually water. So if it's sort of saturated, the amine with the CO2, it goes into a regeneration column, and there you need to heat this amine solution to get rid of the pure CO2. Well, this capturing and regeneration cycle, and particularly this regeneration cycle, it actually implies that you need to heat all the water, which you actually carry around in this cycle. And that aspect is making it very energy intensive. And how energy intensive, it's actually shocking. It's the, you need 30% more energy to burn 30% more coals to use that energy to do this capturing process. So irrespective of the investments, the electricity will consume 30% more of resources if it were coal. So, and that is something you would actually like to avoid, and that is actually the theme of carbon capture. So these parasitic energy costs, that is actually the difficult thing here. And there's some research going on for what you would like to have, but it's sort of difficult to see this number with this particular process go down significantly, and that is something you would like to actually develop new types of technologies to get these costs down, because considering the size of the industry and the amount of electricity being produced, reducing this by significant fractions is an enormous energy saving. Well, this is a typical composition of flue gas. And an interesting question is, what is sort of the minimum energy you anyway need to separate those? And that is using a very simple principle. Your desk never gets organized spontaneously. You always have this entropy of mixing. And in order to get your desk organized, you need to put some efforts in there. Well, that is the same with ideal mixing. If you mix something, it doesn't get spontaneously organized. So this is, in the most ideal case, sort of the minimum energy you need to put in. So you can do this calculation. It's a very easy calculation to do, and this APRI has done this calculation. And what they have shown is, depending on the purity which you would like to have, of how much you would like to capture, whether if it's 90%, depending on sort of the flue gas composition, the higher the flue gas composition, the lower this parasitic energy, but it's about 3%. So irrespective of how efficient your technology is and the investments you make, you will always lose 3% or 3.5% of the energy. So what you can also do is you can sort of analyze what the current chemical industry is using as a measure of these efficiencies. And they usually operate at sort of 3 to 5 times the thermodynamic minimum. And that is a rule of thumb. So if you do this multiplication, you can sort of see that 30% is actually very high. And you would be able to reduce it to 10 to 15% by just looking at the analogy from this is what is done now. But in general, the chemical industry, which has well-developed technologies, they work at 3 to 5 times this thermodynamic minimum. So the potential of energy savings is actually enormous if we develop a better form of carbon capture. The other transparency which is interesting from a CO2 perspective is this one. So this is made by McKinsey, and what they do is they list the various stages of technology. So this is the sort of the technology which is commercial available now. This is in the development stage. Well, if you look at those graphs, say from the bio industry or the pharmaceutical industry, what you will see is actually many, many dots in the concept stage. And this is actually a very interesting observation, and that is there are no new concepts and new ideas of CO2. And the reason is actually very simple, because from a scientific point of view, nobody in his right mind would actually start working on CO2. So CO2 was sort of commonly seen as not a very interesting molecule. So what you see here, all the capture technologies there have been developed, say, 40 years ago, and since then this classical engineering field has sort of been completely ignored. Well, if you turn this situation around, you can also see what you need to separate as CO2 and nitrogen, and those are molecules that are looking actually very, very similar. So if you have a very large molecule and a very small molecule and you need to separate them, it's relatively easy. You have a very different boiling point, so you can do distillation. But here, the properties of the gases are actually very, very similar. So the type of say, technology that we actually need to do is much more subtle. So the question is, can we then use nanotechnology where we have much better control on where to put atoms there to exactly get the right materials for doing these type of separations? Well, and this is sort of the idea we have within this energy frontier research center, but it can also be summarized as creating some dots here. So to get some new materials with much better control on the properties to get this separation more efficiently. So, and this is then the idea. So in summary, we're trying to develop the chemistries to put the atoms at exactly the right place to make this separation as energy efficient as possible. So the topics we are actually studying is two types of separations. One is a separation from flue gases, as I have discussed. The other important separation problem of CO2 is in natural gas. Some of the gas fields actually may contain as much as 70% CO2. For example, there's several very large fields in Australia, and they are not giving a commission to explore those fields if the CO2 is not put back into the ground. Well, if you need this enormous amount of parasitic energy, you need to burn more methane to do the separation than you will ever get out of it. So the exploration, if you cannot do this separation, is not very productive. Well, from a separation point of view, it's also different and interesting. Is flue gas separation is what you call end of the pipe technology. That's simply it's at the end of the pipe, you emit it. It means that the pressure there is very low. So if you want to use a membrane, you need pressure as a driving force to force the flue gas through the membrane, or you need to create a vacuum. So from a separation point of view, that introduces additional energy. Natural gas is actually deep down in the earth at high temperature and high pressure. So there the driving force is for free. So that makes those two cases just interesting to test and develop those materials for. So what is then the idea? We're going to make new inorganic materials, polymer materials, and we have some cross-cutting. It's a characterization team that basically makes sure that the promises the inorganic people make or the polymer people make, that the molecules are exactly at the right place, that they are indeed there and that they do the separation they promise us they would give, and some computation where we try to look at some of the aspects, because the number of materials you can actually make is extremely large. So one of the ideas is you use a solid material. If you have a solid material, you put the chemistry, the same type of chemistry as you have in the amine solution inside those solid materials. The waste recycling of this water, which was consuming all the energy, you may not need, and you may do this process intrinsically much more efficient. And here is this membrane separation, where the driving force is actually vacuum on one side or increasing the pressure on the other side. And that is the energy penalty you have. And you can do some theoretical estimates, and you see with those type of technology, with the adsorbents, they expect up to, say, in the 20% range. If you go to the solid adsorbents, you get up to maybe 15%, or with membranes, you get it in sort of a similar range. And these are the expectation of this parasitic energy. So you see by developing those novel materials for either membranes or adsorbents, the expectation from if you would develop a process with that are actually a significant reduction. So within this EFRC, these are the people that are making the inorganic materials. We have Jeff Long, he is here in Berkeley and also in the material science division. Omar Yagi from UCLA, who has basically made these metal organic frameworks extremely popular. And Joey Zhao from Texas A&M. And well, these are those metal organic frameworks. They are a novel class of materials, but extremely interesting properties. And one of this is this enormously large internal surface. So it's a solid material, and these materials have the world record of internal surface. Well, this is the internal surface you would actually like to use to attach chemically groups that can capture the CO2. So for membrane applications and for other applications, diffusion is also a very important component of how easy the two molecules diffuse in those materials. And by optimizing the pore topology or those openings here, you can actually also play with the differences in diffusion coefficient. So, and this is sort of an illustration of the type of molecular control which we're trying to introduce with these materials. And these are zeolite immetrocolate frameworks, which are a form of metal organic frameworks. And what you're actually trying to do is to make materials with a well-defined pore size. So here you see the different materials and what their pore size is. And the idea is to try to come up with a material where the separation actually requires a certain pore size, and then this is a way of actually making them. In Texas A&M, they have a completely different approach. What they actually do is they make materials where so here you see a cavity where the gas molecules can be adsorbed, and the opening here can be made temperature dependent. So the idea is that you have those molecules open or closed at exactly the moment where you would like to do this capture. So with the idea that you capture it at conditions and then you change the temperatures in such a way that it pores open a little bit more so that the release is much easier. So the idea is that you can go through this capturing and regeneration cycle with far less energy because it just requires a little bit of energy to open those pores and you don't have to heat the water. What Jeff Long is doing is actually this. He sort of looked at the amine solution and said, well, those amines, they capture the CO2 actually extremely well, but I don't want to have the water. So can I now develop the chemistry to actually attach those amine groups at the metal sides of those metal organic frameworks? So you have this enormously large surface covered with amine groups in such a way that you can capture the CO2, but now you have this metal framework and not the water which you need to recycle. Well, developing the chemistry to actually cover the interior of such a material with those amine groups is something that have never been done before, and this is the type of things we're trying to develop with this EFRC. The membrane people are Ting Su, Brett Helms, Jean Flechet, and Francis Zweck. And what they try to do is to make a polymer membrane. So polymer membranes are already used for CO2 separation, but the type of membranes they actually make, it's very difficult to have a well-defined control over the pore size. And that is, of course, what you would like to do. You would like to make materials in which you can exactly control the pore size for optimizing the separation and then introduce some additional chemistry to enhance the selectivity. So the type of materials they're looking at are those hypercross-linked materials where you actually introduce pores by changing the length of these hyperlinks. So if you have short ones, you get small holes and you get something which is only permeable for hydrogen. But if you make them larger, you get actually pores which you may be able to use for the separation of CO2. And what you can do on top of that is sort of introduce some chemical functionality, for example, introduce amine groups at the various benzene components to further increase the selectivity. Another interesting material is this is based on cyclic peptides, which are made here in the foundry. So what they can do is they can make cylindrical peptides, which you can actually see here. They form a hole where you can sort of tune the interactions again by introducing additional chemistry. And what Brett Helm and Ting Su actually have done is they have attached polymer arms to those cyclic peptides, which you can see the gray ones here. And if you put them together, and that is sort of only Ting can do this in the world, I think. If she puts those things together, they spontaneously form such a membrane. And this is a completely new class of membrane materials. Well, whether they're selective for CO2 and nitrogen, that it still needs to be tested. But the first results actually shows that she has been able to make those type of porous material with enormously well-controlled pore diameter and pore sizes. So this is again a new option of making materials. So what you actually see is a lot of options for possible materials. So the group, which is Jeff Courtwright, Simon Teed, Blandine Jerome, and Jeff Reimer, they're actually studying with the ALS, with NMR, and all kinds of techniques, whether we can sort of understand diffusion and the interactions with CO2 with those materials at the molecular level. And there are some questions of how to interpret diffusion results and how to extrapolate NMR diffusion results to something you can actually use in the design of a separation unit. So here it's basically at the microscopic level, you can actually measure very accurately diffusion coefficients, but we do not know yet how to extrapolate those, say, self-diffusing coefficients to transport diffusion coefficients which the engineer needs to actually design a material. So by combining these various techniques, we hope to get some insights in there. The research where Juan, who's sitting here, and I are actually involved in are the computational aspects. And if you just discuss with the synthetic chemists, the number of materials they can make are actually astronomically large, because you have those metal organic frameworks, you have different types of linkers, and they can change the metal, they can change the linker, they can change the type of pore topology. And if you just make a back of the envelope calculation and make the analogy with zeolites, the number of materials they can actually make are many, many millions. So the question we actually have is, can we give some theoretical guidance on how to screen such large number of possible structures in such a way that you can do the synthesis more efficiently? Well, this project has gotten some help from Majid Karanjik and Alice Konings from a NURSE grant and a grant from DOE related to theory. So they're actually not officially part of the EFC, but they work actually on various similar topics. So one of the things we actually have done there is such a screening for CO2 separations in zeolites. And this is actually very typical what we see. We try about 20 structures. Every structure takes about a week of supercomputer time, and we find 2 that work. Well, this is very typical what also synthetic chemists see. It's a lot of effort, and you only find a few. And it's very difficult to address which one is working best. So what we now try to do is with ideas developed in the computer science division, can we use similarity of structures? So we know these work very well, those don't work at all. What is the pore topology here, and can we look at this big database structures that are similar to those that are actually working as a way to screen those structures? So it is actually applied topology what we use here. And it's also used to distinguish elephants that are standing still from elephants that are running. So if you have a picture of an elephant that is running, you can immediately recognize this one is running and this one is standing still. But how to tell a computer that? That is actually very difficult. It's very difficult to make algorithms that give the computer a picture and then ask the question, is this a picture of an elephant that is standing still or that is actually running? So what they do in Stanford, they analyze the topology and make such a picture of it. And they analyze the topology of this elephant and they get this picture. And then you get this third image, which the computer needs to this site. And then it analyzes and say, oh, it's more similar to this one compared to that one. And then they say, this is a running elephant. That's the same what we do with those porous structures. We just look at the pore structure, and then we say, well, these are working very well, and suddenly so this one is working very well, and we get a class of topologies which are actually very similar, and we can test those that actually work, and the first results are actually showing that is actually giving us some efficiency. So, what you actually have here is sort of a design of a separation unit. So what we're actually doing in our EFRC, and this is then on the computational side, is really on the fundamental part. So we know exactly what to do to get some selectivity, but it's for us very difficult to see what type of selectivity you need to get a separation unit that actually reduces the carbon cost to $25 per ton CO2, which is the DOE target. So here you already see some aspects of so for example, in the ETDD division, they have much more sort of information on calculating cost of these processes, and our chemists, they think about how to make those type of materials, and they have no clue what eventually the cost will be. So making sort of this connection is sort of a very exciting exercise, which is in this carbon cycle 2.0. So to make, because if we talk with our chemist, so Jeff Long, he can make so many materials, so why not make one which is actually useful in the end? But actually knowing which one is useful, you actually need to do this completely engineering stuff, and that is not something which is in the Office of Basic Energy Science something they really would like to support. Yet it's very important for us to know. So this idea of this carbon cycle 2.0 is just... So this is the type of sort of research we're doing. This is where we're heading to, and hopefully this carbon cycle 2.0 will lead us sort of the wave of how to get there. Okay. The other thing is, so what hopefully has become clear of this presentation, first, that there is a lot of sort of energy to be gained if carbon capture is done on a large scale, and these sort of new materials will eventually build in, that you can get this 30% down to this 10% level. The other thing you would like to see is, can you integrate, for example, the CO2 capture in the Helios project? You convert sunlight into fuels, and CO2 might actually be a bottleneck if you do that with ambient air. So can you make this link and actually feed the captured CO2 into, say, this process that converts, that puts the energy back in the CO2 to upgrade CO2 to a fuel again? Can you do the same thing with LZ, those kind of things? So capturing CO2 and integrating that with other types of solutions would actually be also very interesting. And with that, I thank you for your attention.
So the amount of absorber would be on the order of all the zeolites now used for oil refining, and the membranes, I don't know, what's the largest membrane application currently? I don't know, desalinization? I don't know. So this would be larger than any of that?
Yes,
Okay.
And by definition.
Okay, are there any scalability issues with making, I mean, it seems abundant materials are used, but are there other scaling things that you need to think about?
Well, for example, with the amine solution, you have these amines are not that stable. So pollution of amines and those
Sure, yeah. Like fertilizers or similar. Okay.
And basically, can you build up the amine industry to match up with this? So and that is also another argument why you need parallel routes and actually think about the application equally early as doing the research.
It's just enormous. Gigaton scale you're really talking about. Okay.
Questions like, if you make metal organic frameworks, chemists think, well, they're marvelous materials because you have all those metals. You definitely, if they're going to try tellurium, you definitely know that's not going to work. But iron probably will be. But are there lists of sort of metal organic frameworks which you never want to use the metal? So if the chemists know those type of information, they can sort of anticipate that maybe mixtures of two metals will do the same as a very rare metal. Okay. But at the moment, they're not realizing that may eventually become a bottleneck.
Well said. Thanks.
And the other thing is, of course, those chemists, they know how to make those materials. They may look at a separation selectivity, but they have no clue whether this separation selectivity is actually desired selectivity to make the design. So this better interaction that we actually know where to go to, but you have seen that with Helios, it's actually very important to have this information, and it's not commonly available.
Thinking about scaling and tumbling.
Yeah.